In today's lesson on space figures and cross sections, we're going to start looking at three-dimensional figures. These three-dimensional figures are polyhedron. The important thing to remember is that the surfaces of polyhedrons are all polygons. What we would consider to be the sides, these are referred to as faces. So this polyhedron has a face here, which looks kind of like it could be a square, a face here, which looks like it could be a rectangle. We have edges, which are the intersections of two of those faces. And then we have vertices, which are like the corners of our box. It's the intersection of multiple faces. Now, as we go through and we talk about polyhedron, we can list how many faces and vertices and edges there are in a particular polyhedron. So if we want to know how many vertices, edges, and faces there are in this one, if we count just the faces, and I'm going to write up here so we have lots of room, I have the bottom, which is 1, and then I have this triangle over here. All right, I have the triangle facing us, I have this triangle, and then I have the triangle in the back. So there are 5 faces. Now in terms of edges, I have this as an edge, 2, and then I have 1 back here, and 4, and then on the bottom, those 4, so I have 8 edges. And then for vertices, we want to count all the corners, right? So we have these 4 corners on the bottom, and then the one at the top, so we have 5 total. Now if we go to list them, all right, if I list the faces, I have the bottom, or the figure, whoops, not B, D, E, F, G, right? And then I have triangle D, H, E, right? I have triangle H, E, F, that would be the right side. If we go to the left side, we have triangle D, G, H. Then if we go to the back, we have triangle F, G, H, right? Now for the edges, those are all of the segments. So if we just start on the bottom, I have D, E, I have E, F, I have F, G, and I have DG. And then if we think of the edges that go up towards the point H, so we have DH, EH, FH, and GH. All 8 of those segments are edges. And then the vertices, those are the points where all of these things intersect. So we have D, E, F, G, and H. So we can count the number of faces, edges, and vertices. We can also list them out. Now for this one down here, we want to know how many vertices, edges, and faces there are and to list them. And then we're going to talk about TV in particular. So let's start with faces. Okay, if we count them, we've got the bottom, right? And let's just list them out first. So we have the bottom, which is UVTW. We have the front, which would be triangle RUV, right? Let's put the triangle sign so we know we're talking about a triangle. We have the back, which would be triangle STW. And we have the only other side, we have the left side, which would be, looks like a rectangle, RUTS, right? So we have a total, oh, I forgot, we have the top. Don't want to forget the top. So we have RVWS. Right, so if we count those up, we have 1, 2, 3, 4, 5 faces. All right, what about the edges? Oops. Okay, so if we just start, let's start on the front face here of RUV. So we have edge RU, UV, and RV. Then if we go to the back face, we have ST, we have TW, and we have SW, right? And then the ones that connect those faces, so we have RS, we have TU, and we have VW, not to be confused with the car, of course. Okay, and so we have a total of 9 edges. If we look at now vertices, these are all of our points. Okay, vertex singular, vertices plural. We have all of our points. So R, U, V, S, T, and W, so we have 6. Now, it asks, is TV an edge? Segment TV, if I put that in here, is that an edge? No, TV is not an edge because it's not the intersection of two planes or two faces of our figure. It could be a segment that we draw in, but it's not actually an edge. Now, as we talk about faces and vertices and edges, we actually have a formula that we can use to help us identify missing numbers if we need to figure it out, and that's Euler's formula. Euler's formula says for a three-dimensional figure, the number of faces plus the number of vertices equals the number of edges plus 2. So we can use that to help us find missing information. So faces plus vertices equals edges plus 2. Here I want to find the missing number of faces using Euler's formula. So I don't know faces, so F plus the number of vertices, which is 20, equals the number of edges, which is 30, plus 2. So F plus 20 equals 32. Subtract 20 from both sides, we get F equals 12. So in this figure, I have 12 faces. For part B, again, faces plus vertices is the same as edges plus 2. So faces is 20, vertices is 12. I don't know edges, and I add 2. So I get 20 plus 12 is 32. That's edges plus 2, so subtract 2 from both sides. Edges is 30. So in this figure, there are 30 edges. Pretty simple. We can also use Euler's formula in 2 dimensions, but it changes it just a little bit, and the reason for that we'll look at in a second. But for a 2-dimensional drawing, Euler's formula reduces to faces plus vertices equals edges plus 1 instead of plus 2. Okay? So if we look at this solid here, all right, we've got a trapezoid on the front, trapezoid on the back, and then rectangles for each of the connecting planes. It says, how can you verify Euler's formula for the solid? Well, to verify it, we're going to plug in the numbers and see if this equality actually holds. So how many faces does it have? Well, it's got the front and the back, top and the bottom, and then the left and right side. So we have 6 faces. Vertices. Remember, these are our corners. So I've got 1, 2, 3, 4, 5, 6, 7, 8 vertices. And then for the number of edges, these are the sides. So let's mark them off as we count. 1, 2, 3, 4. Now this doesn't mean they're congruent. I'm just using that to mark. 5, 6, 7, 8, 9, 10, 11, 12. So we have 12, and then we're going to add 2 to that. So 12 plus 2, I get 14. 6 plus 8, I get 14. Since 14 equals 14, we have verified Euler's formula. All right, that was part A. Now for part B, we want a net for this solid. It's been a while since we've drawn nets, but remember, to draw a net, think of the object as unfolding flat. So I'm going to start with the bottom. All right, that's a rectangle. If I knock the front and the back off, right, it looks like this, and then we just kind of unfold the other sides. All right, so here's the other sides unfolded. So here's our net. And this is going to help us verify Euler's formula for a 2-dimensional figure. This is what it says. Faces plus vertices equals edges plus 1. We're going to check and see. Number of faces I've got has not changed. That's still 6. Okay. The number of vertices might have changed. We're not sure. Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We actually have more vertices because since we've unfolded it, some of them are counted more than once if you compare it to our 3-dimensional figure. All right, number of edges. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Okay, so on this side I get 20. On this side I get 20. Since those two numbers are equal, we have verified Euler's formula for our two-dimensional net. Not too difficult. Now this next part, talking about cross-sections, this is an exercise in visualization, and this is really hard to actually teach. You just have to kind of picture it in your brain, and it takes some practice. A cross-section is the intersection of a solid and a plane. So we could think of it as just a very thin slice of the solid. If I look at this figure, which is a triangular prism, because the bases are triangles, and I take this cross-section, if I imagine it just cutting through, the shape that it cuts out is a triangle. So that cross-section is a triangle. For this cylinder, sliding the plane through the middle, if we visualize that cross-section, if this part right here, it makes a rectangle. If instead I were to make a plane going vertically, so coming straight down through my figure this way, then the shape that it would trace out, like in my triangular prism, would be a circle. So sometimes the orientation of the plane makes a big difference. So if we look at this example, for part A, we want to look at a horizontal plane. So the horizontal plane is going through this way. What is the cross-section formed by that? Well, if I cut through, then if I imagine myself looking straight down on it, what I actually have is a circle. Okay. Now for part B, I want to look at a vertical plane. So instead I'm going to come straight down this way. Well, that's kind of nice because we're already sort of looking at it as if it was cut vertically. The shape that it makes looks like this, right? Which would be a trapezoid. Now, it may or may not be an isosceles trapezoid. If we don't know about these segments here, if they're the same, then it would be an isosceles trapezoid. If they're not, then it wouldn't be. That's not quite as important. The important thing is you have to actually visualize where the plane goes and what it's doing to the figure. Okay.